Okay, let's start. Uh, despite the fact that I'm just doing it for fun, my university professors kind of inspired me to try and put more effort into it, so to speak. So let's see how long I'll be able to keep it up, if even for a little time. So let's recall what we did last time. Okay, last time. proved we proved that in a final dimensional vector space, that is a vector space for which we know that there is a finite basis of this vector space, so there is one at least. We proved that any two bases of this vector space, any two bases of a finite dimensional of a finite dimensional k vector space V have same number of elements. In particular, this number is finite, so they are in particular no infinite bases, right? Have same number of elements. Of vectors. Vectors are elements of vector spaces, right? Have same number of vectors. Definition. I gave this definition implicitly also last time, but let's make it explicit. Definition, this number we call the dimension of the vector space V. Right. So, okay. Last time was already somewhat interesting because I got in trouble doing the proof, and so it was fun to actually discover how it is done. Yeah, I did not expect that it would be fun. I thought that see the proof immediately or something. This was not like that, so it was already entertaining. And let's do something that one always does in the context of linear maps, that's namely their connection to matrices. There is an intrinsic connection, all right? We are already to the point where we can look at that. Well, let's call it, I don't know, let's call it just some observations. It's not a theorem, it's not remarks, it's just some observations. Let VW be K vector spaces and I remind you that K is always same field, so it's vector spaces over one the same field. The K vector spaces are finite dimension. Finite respective dimensions, so finite dimensions, dimension V is equal n, dimension W is equal m, right? Let L from V to W be linear. That is a linear map. If I have something like that, and clearly it is a map, and I want to have a linear map, be linear. All right. Have to check something. Let's see. Oh yeah, that works. Okay, okay. So let this be linear map. Let BV consisting of some one the n, of course, n vectors in the basis of V be a basis of V. So we just take some basis. Doesn't matter which one, right? Let BW W1 to Wm be a basis of W. Right. So and then observe the following. For I in 1 to n, there are a I. Oh well, no, let's make it more according to customs as it's usually written. Oh well, I don't know which is which, but well, let's say AI, something like that. AI1, AIM, and K. Right? I just want to represent each of the 1 to the n with the help. Well, of course, not them, but the images. I want to represent their images, which will be surely elements of W. That's just because the map goes to there. So I want to represent them with those vectors, which is possible because this is a basis, right? Any vector in W can be represented with help of those, and depending on I, so depending on the index of the vector of which we take the image of L, will have different representations coefficients in general, right? That's why AI1, I is fixed. It is now for some L of the I, and this goes through the vectors here. We obtain what? We obtain the following. Obtain L of the I is equal to the sum j equal 1 to m a I j w J. So that's just representation of each such VI, right? All right. All right. All right. What do we do next? Well, observe. Now we could just write it like this. L of V1 L of V n. That's just some abstract vector, right? I can just take those elements and I can write them like in a data sheet, and I can have that, right? No problem with that. And I can now write equal elements in same data sheet. That would be same data sheet, right? No problem with that. Here I will write it out. And W1 plus A1, 2, and W2 plus A1 and WN. If I would go on here, of course, for L of V2, we have then correspondingly the coefficients A with the first index being 2, always kept here, W1, here, okay, again, coefficient by W2, according to this representation, right? So, but 2 is kept because now we are representing L of V2, A2, 2, and so on until A 2 M WM coefficient by WM, and well, what is last? Well, last is N. I mean L of Vn. Here is L, and it is evaluated at Vn, and we have just that stuff, right? N is kept to W2. That's now is just a formal notation, right? I can just write it down, don't know what it means mathematically yet. I'm writing weird stuff kind of in data sheets. Why not? I can do that. I can write it down. The sheet of paper won't have anything, won't be able to object anything what I'm writing down here, right? Why not? Can do that. It's not necessarily mathematical, it's just formal writing down, just like with what we have seen by polynomials. Just formal writing down, right? And now the thing is, this of course doesn't make much sense mathematically, but if we would like keep it up, then somehow formally what arises is, you can see that it is that by formal application of the rules of matrix multiplication, that indeed this is matrix A above, given by coefficients A, multiplied by W1 to Wn. That's interesting, right? Of course, as I said, it's just very informal. We could also even do what mathematicians never do, write this as a vector. Or they do it sometimes if you want to emphasize it. So just like me now, right? We have that stuff. Right. And now what do we want with it? Wow, let me think what I wanted to show you. Yeah, the thing is, let's transpose the whole stuff, right? How do we transpose? Well, let's just uh, switching the columns with the rows. So you should know it because it's a prerequisite that you like are familiar with how you deal with matrices and vectors and so on. So, this is the uh, notation for that being not exactly formal. This here, right? And let's transpose this. Transposing this, it stays equal, of course. So from that we derive. Oh, again, it's just formal notation. I'm not doing really something really rigorously mathematical now. That will come, but for now, just to have some intuition, right? So here you would have A transposed. So transposing applying same operation to equal things doesn't change anything. So transposing that and that, this still stays equal, right? And transposing just means, well, the rows of columns and rows, they are changed. For example, if that matrix was what that matrix was in k n cos m, now it is a matrix in k m cos n, right? So the number of columns is now the former number of rows, and the number of rows is now the former number of columns. And we just take the first row and write it into the column correspondingly to the new dimensions of the matrix. We take the second row, write it into the second column, and that's how it works basically. Of course, from left to right. So we take this, we write that to this column. We take this and we write it into the second column. We take we take this and we write it into the last column. What then happens, the matrix is now we've swapped n and m, and all indices are swapped. So by vector, you just have, for example, n1. This vector was n1, right? Now the dimension is 1n, and first row I write in the first column. When the column is filled, then I write second row in the second column. I write last row in the last column. This is transposition. All right, and that vector also gets transposed. And I don't get tired to emphasize that this is not mathematical. This is just some kind of thinking, right? I like to come up with things like on the fly. That's quite more interesting when you want to arrive somewhere, right? If you don't know yet where you want to arrive exactly. Okay, this is the rule for the transposition, right? Right, if you transpose this, of course, you have to transpose it properly. So this multiplication actually will be this multiplication, right? So, alright, let me think a little bit. I'm transposing that. And that means I want to have this transposed. And that means I have that vector. And that means, of course, if I have transposed the V matrix, and I want to have that as a line, right? So, yeah. Okay. That's that transposed. And that's a transposed. Right. Right. Let's see. Well, the diagonal elements, they of course are the same. Right? We can see that if we write here that, here that, here that, is the same. Well, okay, word diagonal. Yeah, sorry. No diagonal elements, just transposing to one. You see this column, that was the column here, it goes to here compared to the matrix that we had here. So the first column becomes line, just line becomes first column, and things like that happening, right? And that is then, well, we had n lines, so this has to be n, and this has to be 1. All right, the column, so the lines here, and we have the first column finished here. Right, then of course here a, and we have the second column, just keeping the second number fixed. A 3, 2, da da da, a, and 2. So the second column going here, going to here. And then we have here, of course, the last column. The last column was the mth, and here we have, all right, that's of course mth column. The mth column becomes the line, and indeed this entry remains, but the dimensions are changed, of course. And here we have one m. So this is this column. This becomes this line, right? Alrighty. Now something interesting happens. Now let v element v be any vector. I don't write be any vector, but this is just supposed to be meant. You write something like that. Then since v1 to vn is the basis of v, then here lambda 1 lambda n k such that v is equal to lambda I V.I I equal 1 to n. Oh, okay. Then just apply linearity of v to this vector to obtain Just apply linearity by addition and then by scalar multiplication, and you will obtain this. And well, we kind of recognize this thing, don't we? Right, well, more or less. It seems here. Almost. Well, I mean, this is a vector, this is a sum. But if we multiply this sum now by some vector, by the usual scalar product, but in the formal sense, well, let's not call it scalar product, maybe matrix multiplication. We multiply lambda from here. What I mean, now observe that this kind of uses the entries from here. But this is sum. How do we make a sum out of it? Well, that's simple. For this formal equality, let's just write the following. And really, at that point, you should not think about how it has to be mathematically justified, because this is not mathematical. This is just some things for the intuition, right? How you could come up with thinking that we will then justify it rigorously. How you could come up. You don't have to come up with this thinking on that way, but it is one of the ways to come up with it, or at least one way with which I could come up with it now, because it's just fun to come up with it in that way, right? Okay, so I just multiply this vector here into this matrix, and I multiply this vector equal things multiplied with equal things. So we do an equal thing multiplying with the same thing on both sides of this equation, so the equation doesn't change. Again, I emphasize that is a formal equation, but well, let's just do it and look what we get. And sometimes thinking in such a formal, abstract way can lead you somewhere. Well, I don't know if you have already seen it. Well, actually, you have already seen it. Like by integrals in school, you use the product rule and you kind of compute using the well, playing with differentials as if they were numbers. Of course, they aren't, and you can't do that mathematically rigorously, but it can give you ideas. And what I'm doing now is not uh, a way to derive what we will derive. That's just a way to narrate this, right? And I will then derive it rigorously. Of course, I will show how it works rigorously mathematically. It's just a way of thinking, right? All right. So the sheet of paper can't object what I'm doing, no matter what nonsense it is. It's of course not nonsense, but it's just not a rigorous way deriving things, but it is a justified way of thinking. Why not? Because it kind of makes sense in a way, right? Course, you shouldn't write it down, homeworks or something, things like that. But yeah, to come up with things, it works, and this is what I do in my videos. I'm coming up with things in a way that is just occurring to me right in the moment. That's the purpose of that. And what do we see here? Well. We see the following. We see that recall that this is now a matrix that there was a matrix in or it had n it had wait, not here, here it had m columns, it had n lines, so it was, to transposing, it was in n cross m, n rows, m columns. Now it is in m cross n, right, because we have transposed. And hence we can multiply this vector with it and 1 and obtain something in M1. And this vector will be what exactly? Well, let's see what this vector will be. Wow, that will be some sums. Hey, well, this is the first of the M lines. J equal 1. Hey, 1. Okay, wait, should not do that. Should do that. AJ1. And here we have lambda J. Right, so I fixed the first line, so here. Now they are indexed like that. Just look at those numbers, the indices, right? And we go through OJs, just like it is here, and we multiply this by this, right? Each with each, and then we sum. Just matrix multiplication, matrix vector multiplication, but vectors are just special case of matrices, right? Right. I mean, vector notation is just special case of matrix notation. So, and the number of lines is now m, right? And we get here j equal to m. Sorry, because we go to n here, and we go through 1 to m here, right? Of course, a j m here, the last one, lambda j. But well, this is now in k m cross 1. Again, formally, right? Formally, we can't really multiply something with abstract things, completely abstract, unless, well, unless we do it in the formal way, like we can just structurally see how the rules would be applied if it would be somehow admissible, right? Right, but now we have w1 wm and we have some n cross 1, and so this gives formally this sum from I equal 1 to m with this kind of coordinates, right? We multiply w1 by this number. This is just a number in k. We call that those all numbers in k, and that was all numbers in k. So we kind of have a following j equal 1 n a j lambda j. Oh, sorry. Here we go through thrice, of course. So first 1 here, everything 1, this is multiplied by w1, then 2, thing 2, go to j, multiplied by w2, right? So this kind of rises like coordinate. So let's think about that thing. That thing is that thing, right? So if we put it like that, we induce linearity. And what rises here is that. And of course, it's actually a matrix. And wow. Okay, it's a matrix, and W1 cross 1, but of course it's just formal, right? But matrices, numeric formal are really overfilled or over rings we didn't talk about, but yeah, they can be matrices over rings. We just identify elements with matrices, just like here, because this is actually also a matrix, but numbers or like single objects, single entries in one spaces we identify with. So, and if we now follow those formal equalities, we arrive at the conclusion that out of the we would arrive the conclusion, if that would be even mathematically uh, justifiable, if it would make any sense, you would arrive in the conclusion. Arrive at the conclusion that we actually are able to compute the coordinates of the image of V under L using the given coordinates in our V basis of the vector V and some fixed numbers, because this is just representations. Recall that these coefficients were just representations of these fixed elements of W. The picture, the image of V.I under L is just a fixed element of W, and so it has a fixed representation with respect to those vectors here, right? Actually, that representation is fixed. That we have to show yet, and that we'll show in a moment, because I realize now that we haven't shown yet, but it's trivial. It just follows from the linear independence, basically. We'll see it in a moment, that the representation is really unique, that these numbers are uniquely determined. But okay, if we choose now a representation, just for now, we don't know if the representation, if this coordinate of this element of W are actually unique. We have not shown it yet. So just fix representation. And if such a representation is fixed, then it suffices just to know coordinates of this V with respect to the basis BV of V. And with that, we can already compute the coordinates of our image of V in the basis BW. Isn't that great? So that basically means, if I write it down, take coefficients of a fixed, because we find such representation, and we fix it, so we don't change these numbers, and well, yeah, they give a representation of a fixed representations of vectors L E1 L E N W O in W, right? With respect to the basis BW is equal W1 WM. These representations are just given by the coefficients A, right? Like above. Then for any vector V in V, take a representation, and by representation I always mean just the coefficients, right? Take a representation of V with respect to basis BV of V. The coordinates of the image L of V with respect to, and this is just for any vector V we have taken in V, right? With respect to VW seem, because that was just formal calculations here. It was nothing that we have justified. We actually allowed to have those equalities, that we are allowed to calculate like that. That was really funny objects that not necessarily work. But it seems, respect to BW, seem to be computable from that information alone. To that information alone, in the linear way above. That is, it's kind of like, it seemed like those coefficients give a matrix, and these coordinates are multiplied by this matrix, right? So it seems that kind of multiplication with this matrix of our coordinates kind of replaces, when we phrase everything in coordinates in a formal way, replaces the application of our linear map. Well, okay. Let's justify it, because for now it's just some kind of intuition. Wow, actually it would be nice if it works somehow. I don't know if it works, but first, what I forgot to do, this is actually quite important and quite simple. You could have come up with it yourself, but since it is an important cornerstone, let's just do a quick lemma. Given BV one dn basis of a vector space, of a k vector space V, and given for V and V that we have two linear representations for a vector V in this basis, that is I equal 1, okay, and VI let's say VI, okay. Okay. Go 1 to n, VI have A1 AI equal BI for I. That is for I from 1 to n, of course. Right. Proof. If here is I children and 1 to n with AI children minus BI children unequal 0, and then have contradiction to linear independence. Recall that BV is a basis, so the vectors are linear independent by definition. Independence of V1 dn via this is equal 0, but one of the coefficients, at least one, is not equal 0, so this contradicts the linear independence of those vectors. And that's it. Note vectors have unique representation with respect to basis of a finite dimensional vector space. That is what we mean by that. Well, given a finite dimensional vector space, given a basis, we take any vector and its scalar, its representation as coordinates is unique. We call definition. We call such representation for a vector v, for a vector v and v with dimension of a vector space is more than infinity. We coordinates of a vector with respect to the chosen fixed basis. And that is important because with respect to different bases we would have in general different coordinates. You can try to look at that just taking something like, I don't know, just take some basis like the standard basis of R3. Right, that's kind of like a side note. That it is in general not the case that vectors could have same coordinates with respect to different bases. Like such bases are free, setting are free, and take something like this basis. Okay, something very simple. which you could have come up with yourself. Of course, have different the vectors will in general have different coordinates respect to these two bases. Yeah, clearly, right. All right, we have looked at the uniqueness of the representation, and we have defined such scalars coordinates for k vector space V dimension V equal n, the basis BV equal to E1 En. We define coordinate vector, nothing surprising actually. Basis BV for a vector D with, as we know, unique representation with V lambda I I define the coordinate vector of V as such a thing as big phi, and here with respect to which basis we have coordinates, and that is, we just defined, right? It's just a notation to denote coordinates, right? But well, it has something to do with some map structure, as you probably can figure out from this notation that we'll see in a minute. I just defined that to be coordinate vector. Yeah, clearly, clearly we fix the order of vectors in BV and of corresponding coordinates. Otherwise, this vector wouldn't be uniquely defined, right? The vector of the set of those constants that we use in total would be uniquely defined, but the vector wouldn't be uniquely defined because we could just switch the coordinates. We could interchange their places because this is just a set. Here the order is not defined, so we could rearrange them whatever we like. That's why we fix the order of vectors in BV and of corresponding coordinates. Right. That is, if we take another vector, V tilde, and we represent it, we put into the same position in the vector coordinate having the same vector with it, so into same position. In other words, V tilde is equal lambda I tilde I, and then you see vector we put the coordinates in the same order. So the first coordinates will be the coefficient by the first vector here and here. Second coordinate will be coefficient by second here and here. And to say generally, we just say that we fix as how we think of this basis. We fix the order. We always think that the first vector is V1, the second vector is V2, and we give them those attributes of being first, second, third, and so on. Right. So not just numeration, but we give them those structural attributes structurally, so that we always think of coordinates in that way as assigned in order and not just random. All right, and what we did now is actually the way how we will be able to make this rigorous, to make our thinking here that was quite sketchy, to make this really work, to make this rigorous. And we'll see similarities with that, because it's just like I should have replaced these objects by some other stuff. Well, you'll see that. Yeah, that's good that we have seen that, because this is quite more intuitive, in my opinion, than when there are all possible kinds of maps composed with each other. There one can lose oneself easily, but here it is all nice, only that it's uh, completely unjustified that we can even introduce such operations that they have any meaning. But at least here one has the overview, nice overview of what is happening. Oh, if one is familiar with matrices and vectors, but as I said, I presume that you are. All right, but maybe I'll make a course on matrices and vectors. I should do that. Yes. All right. Let me take a moment. All right. Let's look at this. That seems to be a map, because for every vector we somehow have those coordinates. Yeah. Wow. Before we do that, we should take a look at the class of especially nice linear maps. All right. Definition. Let's call it L again. Let L V to W be linear. And now in this definition, we do not restrict V and W to be to have any restrictions on their dimension, because it's unimportant for this definition. Let L from V to W be linear. We call L and better here. Call L a vector space, and in this course it will be always only talk about vector space things. So vector space isomorphism if L is bijective. Recall that bijective means surjective and injective. Injective we had not long ago, and surjective just means that the image, bijective, same as surjective. Plus injective. And injective we had, and surjective is just image of L is whole of W, not just a subset of W, but it's the whole W really. So each vector is reached by mapping of some vector in V, right? And as you are aware, I hope, bijective maps just mean that we really have fixed pairs like V, W from like from V cross W, and really the whole set of this is separated in such pairs in a unique way, right? V, how V, and this pair is taken out. Sorry, not this set, because that would violate the definition of the function, but yeah. Not this set, of course, because, for example, for V, we could have W1 and then we could have VW2. Of course, that's not what I mean. What I mean is just that bijectivity means really one-to-one correspondence. That is, if we have some elements of V here, some W elements of W here, then bijectivity means that via this rule of the map L, we can separate all the elements of V and W using this rule in pairs, where a pair is given by L, D, L, W, V, right? All right. Any V, there is a unique element of W such that L of V is that element of W, and for any element of W, there is a V such that this W is L of V. So if we take those sets, we can just go through them. We go through V, we go through W, and just we take each pair, the L of V, and when we are done, doing that, there are no elements left in neither V nor W, and no pair has same element in any entry, right? So if we take this set, this whole, we really decompose it into disjoint pairs using this rule. Right, that would be this set. All right. Oh wow, it's better, of course, to work with a mathematical definition, but well, intuition wouldn't be out of place either. So now, well, of course, we should have lemma. We recall bijective means that we have an inverse. It's equivalent. Lemma when a linear map L V W and from V to W, and when I talk about linear maps, we always mean that we go from a vector space to a vector space, so I don't need to say that explicitly. When a linear map L, V to W is invertible, which is equivalent to that map being bijective, the inverse map, the map L minus 1 is also linear. Oh, how do we prove that? That's actually a nice proof because it kind of gives you some familiarity, some ways of thinking, right? Proof. Well, let this map goes, of course, from W to V. That's the inverse map, right? Let W1, W2 be any elements of W, lambda any element of K, and so L minus 1 lambda W1 plus W2 is equal lambda L minus 1 W1 plus L minus 1 W2. Right. How do we show that? Well, since for inverse we need bijectivity, here is unique E1 E1 and V such that L of V1 is equal to W1 and same V2 element V such that L of V2 is equal to W2. Then plug it in, obtaining L minus 1 lambda L 1. I just plugged it in here, right? Instead of W2, W1, W2, and here instead W1, W2, just plugged it in. Plus L of V2 is equal. Oh, okay. We don't have that equality actually, so I should not do that. Okay, I won't do that. Okay, what do we get? L minus 1. Just use linearity of L lambda U1 plus 2 is equal to. So let's write plugging in properly lambda W1 plus W2 is equal, right? And here we just use the property that this map is the inverse map of this, and here when we go like that in that pair, then the inverse map does what? Well, it just brings it back. So, and since everything, since all elements are separated in exactly such pairs, well, that means that if we are this element and this element is image of that element under the map L, right? We have this element and this element is image of this element under the map L, then the inverse map does what? Well, it goes back and gives exactly the element to this element of which this element was the image, right? All right, so in particular, if we apply that to that element, we just go to there, to the other side, and then we have to go back to this element because we applied that map. Lambda V1 plus V2, which is just lambda L. Oh, okay. What do we have now? Okay, how do I do that best? Well, from here, just have apply on both sides L minus 1, application of same thing to the equal elements doesn't change anything. So we have V1 is equal L minus 1 of W1, and that I plug it here, I plug in here, right? W1, and same we have for V2. V2 is L minus 1 W2 plus L minus 1 W2, right? So we have shown, and that gives us exactly what we wanted to show for the linearity of this map. Compare this with this, and you compare what we have shown. This is equal to this, right? Right. Okay, that shows the linearity of the inverse map, of a linear map. Right, and now let's make our considerations above figures that were just formal considerations. Right, all right. Definition. Let V be a finite dimensional vector space with dimension V is equal n. Let B V1 Vn be a fixed basis of V. Then define the coordinate map and of course what this map does, it just assigns to each vector its own coordinates, lambda I I equal 1 to n, lambda 1 lambda n, in vector space k n, just like Rn, we have now arbitrary field, right? Fine dimensional k vector space, but all vector spaces in our case are k vector spaces, so I don't have to write it down, but let me write it down. And that goes from our vector space V to that space Kn. Right, well, why did I write it like this and not like this for any vector V? Well, because to define it on a thing that looks formally like this, where lambda i's just go through all possible constellations lambda 1 to lambda n in k, is exactly the same as to define this for a v element v because, as you recall, V was exactly the span of the basis, which is exactly colon and lambda EI. And we can write it in a fancy way, lambda and k. Right. All right. So this is same. If I write this as represented, or if I go through this through elements that have this shape, then clearly this is the vector space V. Just by definition, every vector can be represented in terms of the spaces. But now, additionally, we know that this representation is unique. So when I go through all such representations, I actually go through all vectors in V. Because if I have a vector in V, it has representation. So I went through it, and it has a unique representation. So I go through each vector exactly one time when I define it like this, right? And such a vector has a unique representation coordinate vector, right? So this is same as defining it for any V and V. So I can as well define it for such the IV.I being V, right? Oh, it might be a little funny because when I define it like this, I define that from this expression. So I assign to this expression something. But the thing is, it is just meant that I go through all lambda 1 to lambda n. And that is why I go through the whole space. Now I know it maybe needs a little time to get used to, because it's like funny. I don't say that V is represented like this, but I just bluntly write this, but this is just the space V, right? But I'm myself a little uncomfortable with writing this, because it's like here it is not clear that we go through all of this, right? So, well, I could just define that on that span, and then it is okay, because that is defined to be yeah, okay. So actually what I did, I have defined it on this span, and I have written formula as defined on this span, but I meant by this V, and I'm allowed to, because this span is V, right? Oh, it's just that the notation didn't keep up with the formalization, with the formal thinking here. But of course, you can just think about it in that way, because it all works. But in the notation, that's of course a little bit unnice. But if I define it like that, then I can just say, well, this is the element of the span. Element of the span has this form, and then I just define that for this element of the span to be this. And here I use the unique representation property. Yeah, that's it. Now I get what I didn't like about that. The thing is, if we define it for that, we kind of already use the unique representation property without mentioning it, right? Because if we define it like that, and we define it for those lambdas, what if there would be another lambdas for, well, like for this same thing? But now we know that this same thing really is unique as represented as this expression, right? And since it is unique as represented as this expression exactly, we can define it like this. So that is what I didn't like about it. So if there would be another which one could think, because if it is just written down, it is not written there, it is unique, right? But we have seen that it is unique, And there is no other possibility of lambda I tilde representing that somehow and then giving another thing. So this thing is really well defined. It can't be that we take two different things and they become equal somehow. No, that can't be if we take different lambdas. This is just the contraposition of this lemma above, that the coordinate representations are actually unique if you just take this lemma and you say, well, if you don't have that the coordinates are equal, then the vectors are already unequal. And this is how this all is well defined and rounded up. So I kind of had a feeling that does not work that nicely, but it works because of the properties above. It's just not written nicely, because actually we would have to show that it is well defined, but we have already shown that. Okay, if you couldn't follow that, that's no problem. It's just some subtleties of thinking why things actually work and where they seem to be weird, right? You don't need to follow that. But yeah, it's sometimes useful to think in such ways, even though you know how it works. Yeah, you just see that everything is really so formalized properly. Right, so we define that like that on this space, and we just know that when we take an element from the space, then this element has a unique representation in that way. We have shown that above, and hence we can identify the elements with the representations like this. And then we can apply this to this representation, and we know to what we are applying it. This corresponds to exactly one thing in this set. It can't be different things, right? Okay, we have shown that above. And that is why we can then assign that way to each object represented in that way properly an object of this sort. Right, and that is what we do. Or more simply, just take a vector v, you know it has unique representation, assign to it its coordinates. Right, but well, as I told you, I'm just doing it for fun. So yeah. All right. Claim. Basically, we have discussed that almost or already completely. This thing is an isomorphism of vector spaces, of course. I wouldn't call it a theorem because it's just too clear, right? Proof. Well, first show that it is linear. Proof. IV.D from D to K to the power of N is linear. Oh, why is that? Oh, we just take two vectors, v, w, or you could say we take the representations. You could see those vectors as representations. And what do we get as their coordinates? Well, we know those vectors are represented. Oh, of course, vw element v, and then v plus w gives us via the representations lambda I plus I1 and lambda I tilde. That's now coordinates of v, right? And then we just use like the vector space arithmetics most basic vector space arithmetic distributive law, like distributive law, what else, commutativity and things like that, right, is not even worth mentioning. And we obtain this expression, and we know if it looks like that, this is an element of a field, it's exactly the coordinates of this, because the coordinates are uniquely determined, right? So we took, oh, if you write that down in terms of this map, what we did, if that has this representation, that means that the is mapped by this map to lambda 1, lambda n, right? Now, if W has this representation, then that means that W is mapped by this map to lambda 1 tilde, lambda n tilde. And that is, we know that if it is represented like that, it is the unique coordinate representation of this, because the coordinate representation is unique, and this is the way in which it is represented with respect to the spaces with exactly these coordinates. So these have to be the coordinates, right? If we have such a representation of a vector, if we were able to write a vector down in that way, then that is already the coordinates of that vector. We have shown above that they are unique. So if we found some, then that's already the coordinates. So that here is the coordinates. All right. That 1 plus lambda 1 tilde lambda n plus lambda n tilde. All right. So this is the coordinates of this is the coordinates of this is in Kn, and the equality here is not yet clear, but we have that equality because this is just the rules of how we compute the sum of the vectors in Kn, right? So this is really equality, justified by this equality, right? All right. And of course, by for lambda k v element v have lambda v is equal, that's just same way, right? You can write it down yourself. Lambda I here, you have a representation of that. I have just taken that inside, right? The distributivity or whatever, right? And that is just base coordinates. And you see again that the way how you deal with the coordinates in Kn, it is defined exactly so that this map is certainly linear. Well, not necessarily with that purpose, but it fits. It fits exactly, so you can do it yourself. And it is a good exercise to do it yourself, because I'm not doing it that cleanly. Of course, it is all there, it is all written down, yes, but you should write it down yourself, that here. This proves linearity. Now, bijectivity. Surjectivity. Let remember, surjectivity is we find always a vector that is mapped to the arbitrary thing that we have taken in the value set of the map, right? And oh, this is an element of V simply by the closeness of addition to scalar multiplication, and that is mapped to by that map of interest that is mapped exactly to that, because that is the coordinates of this vector, because that is its representation, as we can see, right? Okay, that's injectivity and injectivity. Oh, for injectivity, just recall that the coordinates are uniquely determined, that this map assigns the coordinates, or we can use criterion that was the criterion for injectivity of linear maps that we have shown, right? Injective kernel of that map is actually subset of 0 in our space V. Oh, that's obviously the case. Let the element kernel of the then the is equal 0 0 in K, and which means recall that it assigns the coordinates, nothing else, the coordinates in the basis, which means that the coordinates of that vector were, oh, actually, to have it written down properly, and you have I equal 1 to n lambda I, the I, the unique representation, right? We know that it is unique from the lemma above, right? And this is exactly just by definition of this map, lambda 1 to lambda n, which means that this is, oh, here's I equals 0. So the map is injective. So we have proven linearity, we have proven bijectivity, so that shows that the coordinate map is an isomorphism. Right, and that is kind of obvious if we have chosen the basis just from what we have observed. The coordinates are uniquely identifiable with the vector itself. So given the coordinates, we know exactly what vector we are talking about. Given the vector, we know exactly what coordinates we are talking about. Right? It's absolutely obvious because a basis kind of determines in the linear way what vector we are talking about. I mean, vector determines in the linear way means it suffices to specify coefficients already. And we have specified the whole vector. Right, but now we have proved that rigorously. And let's do the thing that we had there, right? Well, what we'd like to do would be the following stuff. Now, make formal considerations but identifying mapping by linear map with mapping with matrix multiplication. Rigorous. Right. How do we do that? Let's see. First, recall what we actually did back there. Well, here we have just found out that if we have some image under some linear map L of vector V, we can represent it like this formally. So we can represent it like this matrix multiplication. This is exactly our phi, right? And by these considerations of funny kind, we have arrived at some expression for the coordinates of the image of this V under L with respect to the basis BW, which only involved the coordinates which we now know to be unique of a vector V with respect to the given fixed basis of V and of the vector space V, and the unique representation coefficients of the vectors that are images of the vectors in the basis BV with respect to the fixed basis BW. Right. Now we'd like to justify this, and for that we just need coordinate maps. We don't need anything else because coordinate maps are exactly the way how these things actually become something tangible, right? Because if we apply coordinate maps to vectors, they do exactly that. They produce out of abstract vectors by chosen basis, of course, they produce out of abstract vectors something familiar, namely vectors in Kn, and that those vectors can be multiplied by matrices, can be multiplied by vectors, and so on. So everything will be now in Kn, and those abstract vectors will yield their place to the vectors that are actually proper vectors in Kn, with which all this matrix arithmetics is working. Right. How do we do that? That's actually very simple. Above, we have done some funny stuff, right? Now, let's take same setting. Take exactly the same setting. And let me maybe copy that even. So let me copy that. if I'll find out how to copy here. Okay, well, what did we have? Yeah, okay, I know. Okay, how do I copy? Einfügen, zeigen, beeinflussen. Okay, maybe. Well. Freihand Eingabe. Okay, how do I copy that? That's a very good question. Okay, I don't know now. That's weird because I would think that copying should be the most obvious thing, right? Well, okay. Okay, copy. No, no, no. Okay. Mm, mm, Okay, I'm not sure how to do that. Maybe there's no possibility to copy. Huh. Well, I guess then just let me do it here somewhere. Okay. We do same stuff now, right? We just take V and double, but in your shoes, I would write that down one time more because, wow, it would be not really advisable to just follow the considerations without writing that. Wow, you can make a reference for yourself that I'm taking the assumptions from here. All right, we take again V and W to be k-vector spaces of finite dimension. We take dimension V is equal to n, dimension W is equal to m. We take L from V to W to be linear. We take BV, V1 to Vn be a basis of V. We take BW, W1 to Wm be a basis of W, and then we observe the following. Right. that all does not make much sense anymore. But there's another thing. What if we applied, you see, that funny, doesn't make much sense. But thus far, so LVI is equal to J equal 1 AIJ WJ. Thus far, it works, of course. You see that? Oh, it's just what we have trivially. We have just represented this vector, which is element in W, just like before. We have represented it with respect to the basis BW, right? And now we drew a trick. This didn't work because this was some funny stuff. How could you write abstract vectors in a data sheet in a matrix? Matrix is a data sheet, more or less. Well, yeah. But now we have something cool. We have our coordinate map, which really brings everything into the space Kn, in which matrix multiplication is just a matter with which we are familiar. Just matrix multiplication in a space k to the power of n. Works just like in Rn or whatever. Right. All right. That's what we do. What's that? Okay. We just apply on both sides because it's equal, right? We can do that. We just apply this suitable coordinate map, and now it is the coordinate map that maps the vectors in W to their coordinates with respect to the basis BW. We can do that. No trouble with that. That's the type of map just defined. And we have seen that this map is linear, right? We prove that it is an isomorphism. So we obtain this here. So compare this with this. And now compare this with this. We have now this sum here, which we can write in a matrix because that. Oh, okay, I shouldn't say in a matrix, but we can deal with it in a way. This is now element Km, and this is now, of course, I mean, I should write it down here, W, element Km. But this is not just any element of Km. This is a special element of Km. Which one? Oh. If you think about it, how do you represent this vector with respect to the coordinate space? Of course, it's Ej in Km. That is the vector. What is Ej? We call the usual notation for the vectors in the standard basis, but now our 1 is of course in K. This is just the vector. Zero, 1, 0, and that's J position. Why is that? Well, you have just to think about how you represent a vector of a basis with respect to this basis. Of course, vector wj is nothing else. Yeah, wj, exactly. We want to represent this vector. We want to take its coordinates because this is what takes its coordinates and puts them into a vector in k to the power of n. And this is just the sum of w1 multiplied by 0 plus 0 multiplied by w2 plus 1 multiplied by wj plus 0 multiplied by wm. So that's exactly that. That is the coordinate representation of this vector. And this makes perfect sense. This is just a matrix, which now is what matrix? Well, sorry, that's not a matrix, that's a vector. That's a vector because we multiply a scalar by a vector and we add that up. That's a vector. And vector of what kind? That we'll see now. I is fixed, as you recall. I1, A, I. Yeah. So I have just written down what appears if we evaluate this as the vector, which it is, because it just maps this wj to its coordinates, and we have just multiplied constants by this ones, which is multiplication of vector constant, and then we have added up, and we have gotten this one, right? That is the coordinates of that image of that basis vector will be neatly given in this km as this column vector, right? All right, that's nice. Of course, then it is kind of improper to write this in a matrix because you would have here a vector, here a vector. That's funny, right? But recall this one. We have not only had this, we had this. And that we can do now because if we just write this in a matrix like this, we just write those vectors in a matrix, and those are vectors in Km. So those vectors will give a matrix, right? Just a matrix. And now it is a proper thing because we just take those metrics, they are those vectors, they are in Km, and we can write them in a matrix pretty normally because their entries are now just elements of K. So it's proper matrix, nothing else. Proper matrix over K. And matrices over a field are very well defined, as you know. Right. Right. W L D. Well, what do we have? Right. And now we know that each such is actually that vector, right? And then, of course, this is just elements in K, so this cool. We can write them in a matrix. AI1. I mean A11 because I is now equal to 1. We just look at this and write the corresponding coordinate vector for this chosen I, which is now for this vector is 1, and for 2 that will be 2, and so on, right? A11 here, 1 is fixed, 1. Yeah. So for the second vector we would have A here, 2 is fixed, 2 is fixed here, compare that to that, right? A21, A2M, and that goes on until a whatever n, because that is last one, and 1, and we go again the whole column through the whole column, and we obtain a n n. But this matrix we have already seen somewhere, and we have not done anything criminal, right? We had this equality, and then if we write into two matrices as columns equal things at equal positions, and we just get equal matrices where the matrices are equal in the sense that all their entries position wise are the same, right? Because this is just equal vectors we write in matrices as columns with equal position number. So of course that's the same, because this is just a comparison of matrices in K K whatever K n cross n, right? Km cross n, Km cross n, of course. Km cross n, right? And here we recognize that what we have written down is very similar to this, right? And well, the only thing is we have here this, right? And this we don't have here, but you can think already what that is, because we know already what these representations are. And we don't need this thing, you know, because we could write it here, of course, because we, of course, if you want to have this equality, if you want to keep this equality we have from the equality above, if you want to have this equality, and we want to have something that kind of corresponds, to what we have here, we have to multiply here on both sides, of course, to keep equality, by the corresponding object in our K, in our something with entries from K. What exactly that is, we'll see in a minute. Right? We have to correspond to multiply by something, by thing that is compatible with that by dimension, right? And here we have something in m cross n. We have m columns because we have numbers from 1 to m here, 1 to m, 1 to m. So m rows, I mean, and n columns, 1 to n, 1 to n, 1 to n. So columns. And if we want to multiply here, well, we could multiply by something. That is by way same. Of course, it is equality, and we have written here that was vector in K Km1, and that was n vectors in total, so clearly dimension, but of course because of equality already, right? And of course we could write this multiplication here, because as you will see in a minute why we can do that, and you know what we are about to do, right? Right, because now we want something to bring everything to entries in K, so that we can use our usual matrix multiplication without some weird abstract stuff that is not properly defined. We would have to multiply with that. Let's check the dimension quickly, if it works. I mean, we multiply by that on that side, right? Just like there. We multiply by that on that side. Right. what is that actually? Well, that maps this vector as in km, because we have m coordinates of the representation of this vector in that. But so that is k m1, that is km1, and everything is km1, and we have m vectors. So m vectors in total in the matrix gives that this is m. But we know something more. And of course, here we also multiply by same thing from this side, just to see that this is nothing else but this here. Oh, well, nothing else but this here. But now we have rigorously arrived here without abstract stuff or vectors. Abstract vectors were written in a matrix here or something, or in a row vector, whatever. Just multiply it on both sides, just like that, just like here. Here, the corresponding object is this, where the coordinate map brings everything to the realm of k, right? With suitable dimensions, right? We can also multiply that, so equal things multiplied by equal thing doesn't change the equality, right? But turns out it doesn't change anything whatever, because, well, what is that? Well, of course, also, and blah blah blah. So that's k cross m, and we can see that this is compatible matrix multiplication, element k m cross m from the left multiplied by k m cross n, and that the result is again in m cross n by rules of matrix multiplication here too, right? But what is this? Well, we have had that before. This is E1 and this is EM, which means that this matrix is nothing else but the unity matrix. The unity matrix of that is equal to the unity matrix of m cross m, and the unity matrix, well, if you write this vector here 1, everything else is 0, then you write 0 1, everything else is 0, so you have that diagonal 0 0 0 0, you have that everything 0, right? This matrix, as you know, multiplied by matrix just leaves the matrix the same. So it turns out that in the proper setting, where we have brought those abstract things to something really tangible, really accessible for matrix multiplication, this thing just does not have any effect. So we could write that like that and multiply that by that, but there's no need at all, right? And this is also why here we had not somehow that, well, actually, no, it was already like that. So, but here we had where we had illegals, we had to multiply on both sides. But this does not have any effect at all. That's just nothing. No, of course, there is anyway some abstract nonsense to come up with the idea how it works, so we can cross it because it's not really mathematical, it's not rigorous, it's just to get the idea, right? And it turns out that this just disappears, and now the interesting stuff, that was for now just preparations of how the coordinates of the images relate to the coefficients of representation of the images in the basis PW. But now, the thing that we were interested in was this. We wanted to have an arbitrary vector, and we wanted to have an easy way to compute the coordinates of its image with respect to the basis BW when we have only its coordinates with respect to v, and of course we have those coefficients, right? So let's do that. So let's V element, what element I 1 and lambda I VI element V. We know such representation exists and it has unique lambdas, right? All right, so exactly that. Then again, we want to transform everything into tangible things, which means matrices and vectors matrices and vectors in our K-spaces, right? We get that. Now, of course, we use the coordinate map with respect to the V basis, right? Of course. And lambda, I recall that it is linear V.I, right? And now, this is actually what? This is our lambda 1, a lambda n, right? And this is what? Oh, same principle, representation, that's the I. Yeah, and if you sum that up, you just get this vector again. So you could get it like that, just seeing that it is this coordinates, right? Or you could get it directly from that. And now look at what we had in the abstract setting. We had that equality, right? Because that was that, and then, of course, by linearity, we could just multiply that by that to get that, right? So now we get that. And we have this equality, right? And of course, what do we do next? Let's call this equality double star. All right. By double star, let's recall for a minute what it was. Properly, right? We had that. We had the coordinates of the images of the basis vectors of the fixed basis BV. We had the coordinates of those images of the basis vectors first in the space W, because that's the images, so they have to be in the space W. We had those coordinates written in a matrix, right? Let's just write it down. What's happening? All right, let's write it down. And recall that this was that W star was some quality. And also recall the dimension of that thing. That thing, well, those are the vectors that are in M1, and in total we have n columns, right? Each column contributes one vector, and we have n such vectors at which we have evaluated, right? And that means we have n, we have m lines and columns, right? Then, of course, that is a vector in K n. That is why we can multiply that by that. And you recall there was some equality, right? And then we can just multiply on both sides, but I already write it here, right? And what was on the other side by double star? What we have multiplied by it? Oh, it was this matrix. It was this matrix A11, A21, AN1, whatever. Right. A11, A21, A1, and here, of course, if we have kept that and we have increased that, and we have to do the same. And here we have right, no, here again we have that increase. I'm just writing down the matrix terms here, some tricks to recall what that matrix was. A2, A, and of course we also multiply by that. Right, we just took the equality double star and we multiply on both sides with the same, so it's this equal. Right, that was the equality double star, which we have rigorously derived here. Right. Right, and this we can just omit, right? You remember this and this can just omit because as I am, it was just focus points with what we did there. Right. Right. But what is that? What is that here? Well, just by rules of matrix multiplication obtain and one. Okay, you might be not familiar with this. This is K1, and if you use the matrix multiplication multiplied properly, because this is actually a matrix, this is not a vector with entries, but exactly this comes out. The column with this constant multiplied, and then till the column with this constant multiplied. You can just write it down and out if you would like to really see that it is like that, but yeah, it's kind of obvious, so I don't do that. Right, so and this is just a vector, right? Because this is actually plus. Yeah, that comes out. Of course, it's a vector. This is km1. This is the sum of vectors in km1. So it comes a vector in km1, and you can see this is matrix Mn. This is a vector in n1. So by rules of matrix multiplication, vector in km1 should come out, and this is this vector that comes out, right? And well, what do we have? This is plus, and of course I could take that away because just by rules of identification I could take that away, right? Oh yeah, I could write this and write it down, and you see that we would just have doubled the vector brackets. This has no meaning, right? Right, and now we know what about the sum. Well, we know that the maps are both linear. And well, okay, I won't trouble you with something else that will prove, of course, but next time. Composition of linear maps is linear, so I could have taken that right away because this is composition applied to V1. I could have taken that in right away, but I won't do it, okay? Doesn't matter that much. Composition of linear maps is linear, well, Okay, we'll have it as a demo. I won't do it like that. I'm pretty merciful. Lambda n now when right. This is just linearity of that applied because this is a vector in W, and we have that vector in W multiplied by we have the evaluation of a linear map at that vector in W multiplied by constant, which is bilinearity of this map, because we apply this map to this multiplied by constant, we can plug, we can pull the constant into it, and same, we apply that to that, and that is actually what? Well, here we can apply linearity of that map, and we obtain now lambda in1. Could have done it much quicker, but let's do it like that. Sorry. It's W BW now lambda n. Now you see VBWs are applied at those vectors, and we can see those vectors just as vectors. Those are vectors in W, right? And then we can apply the linearity on the sum. This is a sum, this is evaluations, hence by linearity of VBW, we obtain L of lambda 1. Okay, not lambda, of course, not just lambda. It's different constants. So always different constants and are kept different in general. Lambda n, the n. And finally, not yet finally, we obtain that this thing inside is just equal by linearity of L to the sum. Yes, finally, to the sum I equal 1 to n lambda I vi. So, and what's that? Well, that was the vector v. That is L v, and that is v bw of L of v. That is, this is coordinates of L of v with respect to the basis bw. And what's that? Well, these were the coordinates of v. That is, this abstract identity actually works only that the way to arrive here that these are exactly the coordinates is not this abstract way, but the way where we bring the objects with which we can't deal in the way of simple matrix arithmetics into the realm with where we can deal with the objects which are actually the same, just in another more simple realm, because it is identification, it is isomorphism, coordinate maps are isomorphisms. We actually kind of deals with objects with exactly the same structure in how they behave, but we deal with them in a realm in which we can deal with objects in the ways of arithmetics, or well, matrix arithmetics. And this is a useful principle of mathematics, that when you can't deal with some objects in a way you'd like to deal with them, but it kind of seems like they exhibit a structure that allows dealing with them like that, like you'd like to, you just transform or bring them into a realm where they appear in a shape where you can apply the things you'd like to apply to them, or where you can deal with them in the way you'd like to deal with them, which the structure kind of suggests. And sometimes you alter those objects a little and things like that. Here we had direct identification, so we didn't need it, but this is a general principle of mathematics, okay? So what we have arrived at is actually the following. What results from that is the following. To compute the coordinates and not some abstract stuff, of the image of any vector v in V under the map L, we just need its coordinates in its home basis, that is in the basis BV, and we need the coefficients of representation of the images of our vectors in the basis BV with respect to the basis BW in the target space. And the computation happens by the way of the matrix multiplication on the coordinates, right? And you recall that what is actually written here, maybe I'll write it for you more explicitly. A1M. Here you have A1M. Here you have A12. Here you have A13, and so on. Here you have A22. Here you have A23. And maybe you already recognize what is actually written here. What was that? Well, what was that? What were those representation things? Let's look at that. We go through J from 1 to M, and I is kept fixed. For example, I is equal to 1, and we go through all J's in the second index. So A1, and we go through 1 to M. A11, A12, A12, A13, A14, until A1M. This is that thing here. Oh, well, better. Okay. Now, where would we like to have it? Here, A11, A11. That is this column is exactly the coordinates written in the column by which we represented L of VI, the image of VI under L, with respect to the vectors in the basis BW. That's exactly that. A11, A12 for vector V1, or for vector VI, AI1, A1, AI2, AI3, until AIM. That's exactly this representation. That is this. Is nothing else but what we write into this column is nothing else but simply and we write it as a column here, right? We write just the coordinates of that with respect to the target basis, so to speak. All right. And this is great, right? That matrix is, of course, in K, M, cross. Right, and that thing which we have derived here to be equal, that thing here is equal to that thing here, that thing here, equal to that thing here, which I have written exactly here, or almost. All right, just those equalities, right? Which lead us by way of those equalities, we arrived at, right? Start here, which is exactly that here, right? Which is exactly that here. We took this matrix of those representations, which is what is happening here, right? Then it was equal to this. Then we got here by way of matrix maturity. Then we got here, 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 and finally it was equal to here, which is here, right? That is really the application of a linear map L is same as matrix multiplication when the bases are chosen and the coordinates with respect to the domain bases are given, right? If we have those representation vectors, if we know, and if we have a linear map, and this map is defined, so those images are defined, the images of the vectors in the basis, and we write those coordinates of the images in this matrix. And if we want to compute coordinates of the image of a vector v in a vector space v, this is this coordinates, we just multiply this matrix that we have written down that way by the coordinates of that vector with respect to the chosen basis, right? And that this is indeed coupled, that it is not independent somehow. Well, we take this coordinates with respect to this basis, and these things written down here, they are with respect to this basis. Particular with respect to another base, we would have completely different things. So both bases are fixed for something like this, right? And this can be identified with this matrix. But of course, since the bases could be chosen completely differently, it's not actually identification with this matrix, but it is identification with identification with any such matrix and with all such matrices simultaneously. So the choice of the basis decides with which matrix we identify it currently. Right. So this is a big thing, and this was really fun because, well, we started really abstractly and then we arrived at some really interesting stuff, right? And you should note that, and I should note something, not theorem composition. You could prove it yourself, but okay, I'll prove it for you. Composition of linear maps is linear plus, well, whatever. Okay, let's see. Not theorem composition of linear maps is linear plus. Examples for alrighty. That was big, right? It's really cool. But okay, that's it for now. Thank you very much for your attention, and I'll see you next time.